All right. Well, it's now the second week of school and it's Monday, so happy Monday, you guys. Um, let me, sorry, let me pin my own video. Switch back to gallery. Okay. And then I think my screen's being shared. Okay. So we are going to talk about Monte Carlo integration. So I've decided to go slightly out of order. So this is the one of our textbooks, Introducing Monte Carlo Methods with R. So the other textbook is about Bayesian stuff, and we'll revisit it later. But then we're gonna take a look at this one, Introducing Monte Carlo Methods with R. Now this textbook, and again I've linked it in the syllabus. It's very, very, very dense. Okay, so I will spend like an entire lecture on material, and that entire lecture of material will be like 2 pages or a page and a half. Okay, so it's just the book kind of just talks about stuff and then it lists an equation, and then it's just like every time it lists an equation, it's kind of just like, well, duh, that's like there's a tendency in math textbooks to just kind of say like clearly this, or just that this is going to happen. So I'm going to have quite a few slides, but we're really only going to get through maybe it's going to be like 2.5 pages on here, and I think that's okay. We'll cover at our pace. I think it's an appropriate pace. Okay, so this topic is Monte Carlo integration. All right, and so on Friday of last week, we ended our lecture with the baseball example, and you guys have been working through the baseball example in your homework, and this is really just kind of a very early intro or basic intro to kind of some Bayesian concepts where you have a prior distribution. So this is kind of a brand new player. We don't know anything about this specific player, but we do know something about players in general. So we have a prior distribution to kind of describe players in general. And then we observe some data from this particular player. And then we update our distribution, our posterior distribution, for what we believe about the player. And so with the beta distribution, it's not too hard. You just kind of add numbers to your alpha and add numbers to your beta, and it just works out quite nicely, right? But then if you were to ask another question, such as, if this player has 3 at-bats in the next game, what's the probability that he gets exactly 2 hits? Then the answer is going to depend on that value of theta itself, which is a random variable. Okay, so the answer to this question, what's the probability he gets exactly 2 hits in 3 at-bats, that's going to be a binomial thing. 3 choose 2, theta squared, 1 minus theta to the 1, but it depends on theta, which is a random variable. And on Friday, we talked about a few ways or a few strategies to handle this. And we said one is you can just kind of pick a single value, such as, use the mean of theta or the mode of theta, or you can kind of take the integral of this. But in this class, we said we're going to avoid the integral and use Monte Carlo estimation. And so in our class, we're going to estimate it. Okay, we're going to get we're going to estimate the expected value. Okay, so again, because it's a random variable, the actual answer could be anything, right? It could, the true answer could be much higher, much lower than this, but we're going to try to estimate the expected value of it. Okay, and if we wanted the true expected value, the expected value of that function g, when applied to the random variable x, we would get this integral, the integral of g of x times f of x dx. Okay, and this relationship is known as the law of the unconscious statistician. You can, you know, maybe I should add that text, but this is law of the unconscious statistician, and we are going to estimate it using just kind of the mean of the sample mean, or basically just the mean of kind of the result of applying the function g to a bunch of samples x sub j, okay? So xj are a bunch of values that we randomly draw from a distribution with this particular PDF, okay? And then we take the mean of it, right? And so I think I've finished Friday's lecture with this. We said f of x is the PDF of the beta distribution with this. And so we're going to use r beta inside R to randomly draw values from that distribution. Okay, and that's what I have here. So I got R beta. I asked to draw 1,000,000 values with these properties, 86, 224. And then G is this, 3 times theta squared times 1 minus theta to the 1. So this is going to do this, and I apply G to all the values in my sample, and then I take the mean of that, and I get this, 0.16715. Okay. All right, so this is our estimated value. On Friday, we also worked through the analytic solution, but here we're just going to take a look at the Monte Carlo value. All right, so we're going to take a deeper look at this, and so on this slide, just to kind of match the notation of the book, I'm going to swap the letter G with the letter H, but it's exactly the same. Okay, but this is the notation that we have in the book on in section 3.2. Maybe I should pull up the actual PDF. Okay, so this is, here it is in the textbook. So just to kind of match this, this is what we've got. All right, and all right, and so this notation is a little bit funny, okay, or it's a little bit complicated, and so this we say this is the expected value. That's the E part, the expected value of the function h applied to the random variable x, okay? So it's the expected value of the function h applied to the random variable x, right? And x has a distribution defined by the PDF f, okay? So when you have this distribution f, this is the expected value. This is the expected value that you get when you apply h to this random variable x. All right, and this, by kind of law of the unconscious statistician, this basically is this, okay, but it's got the letter G, okay, but expected value of g of x is basically g of x f of x dx here, okay. And this whole thing can be approximated by the mean of a sample of, you know, a bunch of values drawn from the density f. So we're going to take xj, which is going to be a bunch of values drawn from the distribution f, and we're going to take the sample mean. All right, so a little bit more on notation. Okay, so x is a random variable that comes from this distribution defined by, comes from a distribution with this PDF f of x, and this is what we say, you know, for x being inside, this is the kind of the domain or the support of x. Okay, so this region, curly, you know, fancy x down here is the support of x. which means that the PDF is greater than 0, wherever x is inside that support. And if it's if there's no support, then that means the PDF is equal to 0, right? So that means we're never going to draw that value. So if you think about like the beta distribution, everything outside of greater than 1 and everything less than 0, you know, is outside of the support of x. Okay, and therefore, if you integrate just f of x, you're going to get 1, right? And then and the expected value of x, you know, is the expectation of x with a density function f, and that would be equal to the integral of x times f of x dx. Okay, so anyway, the steps to summarize classical Monte Carlo integration is going to be this, right? So this is a bit of a big if, but if we are able to sample directly from this density function f, then we can estimate this value just as follows. Generate a whole bunch of x values randomly from f of x, all right? So this is kind of the Monte Carlo part. We generate them identically, independently and identically distributed from f of x. So in R, that's made simple for a lot of common distributions using all of kind of the R family of functions. So R beta, R binom, R norm, any of those functions would work. And then you're going to basically compute. You're going to apply that function h to every single value you've drawn. So you're going to compute all of this. And then you're going to estimate this quantity by taking basically the mean of all of those values. Okay. And so this right here, h bar sub n, is the Monte Carlo estimator based on n values. Okay. And so this is what we call the Monte Carlo estimator. All right, let me, I guess I just want to kind of make sure everything's okay. So far, so good. Maybe. All right. Okay, your first quiz answer today is the letter A. Letter A as an apple. A as an apple is your first quiz answer for today. Okay. This is very far from a formal proof, not a formal proof, but I'm hoping to provide a tiny bit of intuition here. All right, and so, you know, how does this thing work, right? Like, how is just taking the sample mean of h applied to x going to estimate the kind of the true expected value? Okay, so h bar n, this is just the estimate of this quantity, and we call it the Monte Carlo estimator, right? This is the Monte Carlo estimator. And then this subscript n kind of basically means it's based on n observations. So subscript of like 10 would be based on 10 observations. Subscript of 1,000,000 would be based on 1,000,000 observations. Okay, and so this is how we estimate this quantity. This is an estimate of this quantity. You know, this quantity requires us to do this integral, and in some cases, this integral might be very difficult to pull off. Okay, so we're going to estimate it just by generating a bunch of these values. All right, so this is not a formal proof, but as we draw more and more values, okay, we can expect the sample that we have, the sample of all of these random draws, to become more representative of the distribution that we've made by that density function f. Okay, so as we get more of these random draws, we can expect kind of this sample to become more representative of the density function, right? And I think that makes intuitive sense that, you know, the more you draw, it's going to look more like the real thing, right? Okay, and technically, I guess a little bit more formally, it means the empirical cumulative distribution function, and we'll talk about what exactly this is. The empirical cumulative distribution function, which is given by f hat, big F hat, sub n. So this is big F hat, kind of the estimate of big F. Big F is usually, if little f is your density function, big F is your cumulative distribution function. And so I've got big F hat, okay, subscript n. So it's the empirical cumulative distribution function, or the estimate of it, based on your sample. And that converges almost surely to the actual cumulative distribution function. Okay. I don't think I don't know. Have you guys learned about like modes of convergence? Was that covered in any of your classes? Maybe, maybe not. Okay. If you go to grad school for statistics, you will certainly have to, at some point, talk about modes of convergence. And that was the class that in grad school, that was the class I almost failed. Or I probably should have failed, but I feel like the professor mercy passed me in that class. And so it's hard. It's like a bunch of like formal math proofs, and there's different ways of like how a random variable converges to another thing. And so anyway, almost surely is one of the methods for convergence. There's like converges in probability, converges almost surely, converges surely, I don't know. And they all kind of mean the same thing, but there's like different implications. And so anyway, it was hard for me, but anyway, that's what I've got here, this little arrow. So if you go to grad school and you struggle with how your modes of convergence go, that you're not alone. And hopefully you have a nice professor that supports you. Okay. All right. So anyway, what's going to happen, because because our empirical cumulative distribution function converges to the true cumulative distribution function, based on our sample, then the expected value of h of x is also going to, our estimator is going to converge to the true value of this. Okay, right? So this is an estimate of this, and it will converge just as well. Okay, so here I wrote this based on the sample converges to the actual CDF. And so I just want to kind of explore that a little bit. And so have any of your classes covered empirical CDFs? Empirical cumulative distribution functions? Okay, no. All right. It's very simple, okay? It's, so here, we will talk about this, right? So if you look up what is the empirical CDF on in Wikipedia, you're gonna get some definition like this. Yeah, it's got like more math. Like Wikipedia pages have a surprising amount of math in some of them. So basically, you've got a whole bunch of random variables, okay, right? You got random variables that have this cumulative distribution function. So that means they all kind of have the same PDF, right? And if the integral of the PDF is the cumulative distribution function, right? The formal definition of the cumulative distribution function is basically the probability that some random variable x is less than some value t. And so the cumulative distribution function always starts off at 0 when t is negative infinity, and it climbs up to 1 by the time t gets to infinity. So, for the normal distribution, it's close to 0 when, t is like -3. And then by the time t gets to +3, it's close to 1. For the uniform distribution, it's basically just a straight line going from 0, 0 up to 1, 1. And, you get this diagonal line and things like that. Okay, so the empirical CDF is basically based on this, except it's based on your sample. So it's just going to be the number of elements in the sample that are less than t, and divided by n, okay? Oh, maybe this needs to be less than or equal to, okay? The number of elements, well, I'm trying to remember. Is it less than or equal to? But anyway, it's the number of elements in the sample less than or equal to t, divided by how many elements are in your sample, all right? And so we can see that this is basically an empirical estimate of this, right? So what proportion of values are less than 2? You know, you just kind of, you can get your empirical value versus the true probability, right? So we're just estimating this based on how many elements we have in our sample, okay? So, oh, and this is just a note, you know, in R, I think you guys know this, but D is for density, P is for cumulative probability, and so the CDF is drawn by P whatever, so P norm is going to be your CDF of the normal distribution. So P norm of 0 is 0.5, and then Q is the inverse, so when you do Q norm of 0.5, you're going to get 0, and then R is for random, so that's where you get your random values here. Okay, so anyway, this is what the empirical CDF looks like, okay? So here I'm going to draw 5 values from the random uniform distribution. And so that's going to spit out 5 values between 0 and 1. And if I sort X, this is what I get. I get 0.2016, 0.2655, 0.372, 0.572, 0.908, okay? And so your cumulative distribution function, notice that it's got the function starts off at 0, okay? And we're basically asking what proportion of values, right? So this is, it's the number of elements in the sample that are less than t, okay? So how many elements are less than 0.2? 0. No elements are less than 0.2. So as I'm going up x or t, okay, none of the elements are less than this. And then as soon as I get to 0.201, what's the, I have one element that's less than 0.201. And so my empirical CDF is going to be 1 divided by 5. And so that's 0.2, okay? And then it keeps going. And then as soon as I hit 0.2655, okay, so at 0.266, how many elements are less than 0.266? 2 out of 5. So my empirical CDF jumps up to 40%, okay? And then it goes up to 0.372. So at 0.372 or 0.373, the thing asks how many elements are less than 0.373. 3 out of 5 elements are less than 0.373. So my empirical CDF is now 0.6. And then at 0.573, 4 out of 5 elements are less than that. So it jumps up to 0.8. And then we've got nothing between 0.573 and 0.908. So, you know, for how many elements are less than 0.7? 4 out of 5. How many elements are less than 0.8? 4 out of 5. How many elements are less than 0.9? 4 out of 5, 0.8, okay? But then at 0.91, how many elements are less than 0.91? 5 out of 5, and so my empirical CDF jumps up to 1, okay? So this is basically an estimate of what your cumulative distribution function looks like based on whatever sample you have, right? And so, you know, we can see that this is, with only 5 elements, your empirical CDF is not going to be very accurate, okay? And you've got these big steps here, okay? But, and if you compare that to the true CDF, okay, the true CDF is going to be P of the uniform distribution, so P unif, okay, that's going to be the cumulative probability. That starts off at 0, and then it goes up to 1 by the time it reaches, by the time t reaches 1. So when t reaches 1, the cumulative distribution function is equal to 1, and this is what we have. Yeah, so so it should be less than or equal to. So I'll have to go in and correct this to be less than or equal to. Okay, so this is what we have. And so let me just kind of show you what happens as I bump up my n. So this is your CDF based on 5 values, okay? Here it is based on 10, okay? And so we can see, you know, I just pulled 10 random values between 0 and 1. And, they're not evenly spaced out. When you draw random values, that's the thing, they're random. And so some values are close together, like these three are close together. But these two values, like I didn't get anything between basically like 0.65 and 0.9, okay? I didn't get a 0.7 or 0.8 or 0.85 or anything like that. So I've got kind of this wide flat region. But overall, we say, and so in this case, because I've got 10 values, my cumulative distribution function, my empirical one, jumps up by steps of 0.1 at a time, right? So it's asking how many elements in my sample are less than this particular value. And it's going to start off by saying none of the elements are less than that value. 1 out of 10, 2 out of 10, 3 out of 10, 4 out of 10, 5, 6, 7, 8, 9, 10 out of 10 values are less than that value, okay? And so the empirical CDF is always going to be a step function, but the idea is that as you increase n, as n gets bigger and bigger, the size of the steps between random values is going to get smaller and smaller, okay? And ideally, as your samples increase, there's going to be more lineup between the empirical CDF, which is this step function, and the true CDF. Okay, so here it is with n equal to 10. Here it is with n equal to 100. So now there's 100 steps. Okay, and it's not perfect alignment, but it's getting better. Okay, here it is with n equal to 1,000. And so the empirical one is in black versus the true CDF, which is in red. And we can see that they're starting to line up pretty good. So I don't know when R decides to drop the dots, but it does. At some point, it drops the dots, okay? And it kind of connects them all. And so there's, we picked 1,000 random values, okay? And in this region, there happens, when the slope is a little bit steeper, these values are a little bit closer together than we might expect. And then over here, the values are a little bit slightly more spread out over here. But anyway, we get something, we can see the empirical CDF lines up quite closely to the true CDF, and that's with 1,000 values. And if I go up to 10,000 values, 10 to the 4, we get something that lines up quite closely, not perfectly so, but quite closely. And it kind of just supports the idea that as n increases to infinity, then the empirical CDF is going to converge to the true CDF. Okay. I do the same thing, just also to demonstrate for a different distribution. So this is the normal distribution, and I start by drawing 10 random values, and and it asks, what proportion of values are less than, something, and your empirical CDF is kind of way off. But as you draw more, we can see our empirical CDF, this is with 100 values, aligns a little bit closer to the true cumulative distribution function of the normal distribution. And here it is with 1,000. Okay, it's getting even closer. And at 10,000, it's very close. Okay, so there's, it's not perfect, but it gets pretty close. Okay, and this is this is one way to kind of evaluate if if the random numbers you've generated are coming from the distribution that you want them to come from. Okay, so that's the empirical CDF, and what we're trying to show is that this thing converges to the true CDF, okay, as n increases, and that kind of compels part of the reason for why our Monte Carlo estimator works. As our sample size increases, our Monte Carlo estimator works there. Okay, so yeah, this is all we said. So as n gets larger, we can see that the empirical CDF, based on the sample, gets closer and closer to the actual CDF, right? And the pictures that I've shown you, they don't make a proof, but hopefully they provide a little bit of intuition behind the idea of using a large sample of random values that to kind of approximate the function applied to a random variable. Okay. Yeah, the formal proof is hard or is something that I struggled with. Okay, especially on like a closed book exam. I was like, oh my goodness. Okay. All right, so let's talk a little bit about some of the properties of this Monte Carlo estimator. Okay, so first, the expected value of the Monte Carlo estimator is the true value that we're going for. I guess I could have subscript F here. All right, and so, you know, the math behind this is that the expected value of this is going to be the sum of all of the values that we get. Okay. And, you know, the expectation of a sum is also equal to the sum of the expectations. And all of these things, all of your x of j's are basically just the same random variable x. And so, so if we have n of these, if we're going to sum up 1 through n of these, we're going to have n times the expected value of h of x, and that's going to cancel out the 1 over n. And so we're just going to get this. Okay, this is very much kind of like if you look up the proof of like why the sample mean is an unbiased estimator of mu, it basically looks like this, but it's basically the sample mean of this function h is going to be an unbiased estimator of the value h. Let me give you your second quiz answer. Second quiz answer is the letter E, E as in elephant, E as in elephant for second quiz answer there. All right, so that's the expected value of the estimate. All right, and let's talk about the variance. So the variance is a little bit messier. Okay, so again, this is the Monte Carlo estimator of this. All right, so we are estimating this, or we're estimating this by using this. Okay, and we want the variance. What is the variance of this estimator? Okay, so the variance of this estimator is going to be the variance of this whole thing. All right, so we got the variance of the sum, and I'm going to expand that sum. So I've got the variance of basically all of these terms. Okay, from I'm sorry, this should be j equals 1. Sorry, this is a typo. From j equals 1 to n. That's the same typo right there. J equals 1 to n of all of these. Okay, and okay, and so whenever you have a constant multiplied by something in the variance, if you pull out the constant, it becomes the square of the constant, right? So if I pull out 1 over n outside of the variance, I'm going to get 1 over n squared. Okay, and we're going to have we can kind of break up this sum, variance of the sums, into kind of the sum of all of these variances. So each of these things are going to become 1 over n squared times the variance of h of x, and we got 1 over n squared times the variance of h of x2, 1 over n squared times the variance of h of x n. Okay, and all of these x sub j's, okay, all of these things, x1, x2, xn, these are all IID. Okay, so they're all going to have the same variance as well. Okay, and all of the h of these are going to have the same variance. So the sum of all of these things is going to become 1 over n squared times n times the variance of all of these things, and we're going to get 1 over n times the variance of h of x. All right. So this is going to be the variance of this thing. The variance of this is going to be 1 over n times the variance of h of x. So this is very similar to, you know, what's the variance of the sample mean? The variance of the sample mean is 1 over n times the variance of the population, right? Okay, now if we wanted to estimate this, right? So what is this variance? Okay, this variance, the variance of h of x, that is probably unknown to us, right? You know, what's the variance of h of x? That's going to be unknown because we probably don't even know what we're using h bar sub n to estimate the expected value of h of x. So if we don't even know what the expected value of h of x is, I doubt we're going to know what the variance of h of x is. Okay, so we can estimate the variance of h of x. Okay, so we can get a Monte Carlo estimate of this variance. All right, so this right now, this is just the variance of h bar, the Monte Carlo estimator, which is 1 over n times the variance of h of x. And then now we get the this crazy title here. This is the Monte Carlo estimate of the variance of the estimate, if that's okay. Is that all right? So we want to know what's the variance of this, okay? But the variance of this depends on the variance of this thing, which is going to likely be unknown to us. So we're going to try to estimate what the variance of this thing is, all right? So now I've got the estimate of the variance of the estimate. Is that all right? I hope that's okay. All right, so if we don't know the variance of h of x directly, right, then we can estimate it using the Monte Carlo identities and Monte Carlo methods, okay? And so and we just say, well, what's the definition of the variance? The definition of the variance is this thing, okay? It's basically like if you say, what's the variance of y? It's going to be each value y minus the mean of y. So you take, you know, y minus the mean. So you're getting kind of the distance, square distance from the mean, the expected value of the square distance of the mean, right? So you do y minus the mean of y squared times f of y, right? So this is just the definition of the variance. I hope that's okay. We've learned this, right, from in 100B. Okay, so so if we have that, all right, if y is going to be h of x, then the variance of this, which on the previous slide we established is 1 over n times the variance of h of x, we're going to replace the variance of h of x, okay, and we're going to allow y to be h of x. This becomes h of x minus the expected value of h of x. We're going to take this quantity and we're going to square that, and we're going to multiply that by f of x dx. And we're going to take the integral of all of that. Is that okay? I'm just basically replacing the letter y here with h of x. And so this is what I get. All right, is this okay? All right, so how do I solve this integral? Okay, we are going to estimate this integral using Monte Carlo integration, right? So I'm going to just say, let this portion of the function be equal to g of x. Okay, we're going to just say, let this entire, whatever this thing is, let this entire thing just be the function g of x. Okay, and so if you do that, this be, you know, the integral of g of x f of x dx, we said that's given by the Monte Carlo estimator, where you take samples of x drawn from f, and then you apply g of x to it, and you take the sample mean. All right, so if we do that, then this becomes, the variance of this is going to become 1 over n times 1 over n times this, okay? And so I got 1 over n times 1 over n, and then g of x is just this function here. Is that all right so far? Okay. All right, and then, okay, so then how do we do this? Well, so we've got this, and we are going to replace this quantity, again, which is unknown to us. We're going to just replace that with h bar sub n. Okay, we're going to replace that with h bar sub n. And so with this, we're going to call v sub n kind of the Monte Carlo estimate of the variance. Right, so the true variance, the variance of this estimate, can be approximated by Vn, which is going to be 1 over n squared times h applied to each value x minus our Monte Carlo estimate h h bar sub n quantity squared. Okay, so this is the Monte Carlo estimate of the variance of the estimate. We're estimating the variance of the estimate. Right. So an analogous would be kind of like in the central limit theorem. You have x bar is your sample mean, and what's the variance of the sample mean? That's going to be sigma squared over n. Okay, but then if you don't have sigma squared, you have an estimate of that variance, and that's going to be s squared over n. Right. So it's kind of like that, except everything's based off of Monte Carlo estimates. All right, so so now we've got the variance and the expected value. And if you look at this, if you look at what h bar is effectively a sample mean, right? There's a big sum. It's the sample mean of h applied to a random variable, but it's basically a sample mean, right? And because of that, so you can use the central limit theorem, right? So the central limit theorem can be applied to anything that's a sample mean or a sum, you know, something related to a sum. And so so if, you know, the central limit theorem says that if you got the sample mean y bar, then its sampling distribution can be approximated with a normal distribution with mean mu and variance, you know, s squared over n. Okay, and so we're going to have h bar comes from this normal distribution where the mean is this expected value, and the variance is going to be 1 over n times the variance of h of x. Okay, and we showed that this can be approximated by Vn, and this is what we have here. Okay, so h bar sub n can be approximated with this normal distribution with this expected value, and this we can estimate our variance using this. All right, and knowing that this is normally distributed around the true mean allows us to kind of create confidence interval bounds. So we can create a confidence interval for the expected value based on kind of our sample mean. Okay, so there's a whole lot of stuff here, but I don't want you guys to get lost. Okay, so this is just the important things so far. Okay, the important things that we've covered today so far is that we have, if we can sample values of x from f, we have a way to estimate the expected value of this function, right? So we can estimate this expected value using our Monte Carlo estimator, all right? And this is just the sample mean of h applied to x. And it works because of the law of large numbers. And then, and this estimator is normally distributed, and we are able to estimate the variance, okay? So that's all we're saying. So let me just run through a quick application here. Maybe we'll run out of time, but we can use this. So one application is that we can use the Monte Carlo estimator to approximate any integral or an integral of any function. Okay, so as long as it's on a closed interval, so it's not going to work if it goes off to infinity. Okay, but as long as you've got a closed interval, the integral from a to b of any function h of x can be estimated. Okay, so we've got h of x dx. Maybe this function is too hard to integrate. Okay, well, we can say, well, the average value of h of x over the integral a to b is going to be basically, you take the integral of h of x from a to b, and then you're going to divide by the width, by that distance from a to b. So you're going to divide by b minus a. Okay, so you're going to do 1 over b minus a. This is going to be the average value of h of x. Okay, And so just by rearranging some terms, okay, if I move this 1 over BA inside here, okay, then I've got h of x times 1 over b minus a. And if I let f of x equal to 1 over b minus a, then f of x is the PDF of the uniform distribution from a to b, right? So the PDF of a uniform distribution is just a flat line, which is equal to 1 over b minus a. Okay, so I'm going to just move this inside, and here I've got h of x times f of x dx, and that's going to be equal to this. All right, so this is just our Monte Carlo estimator if we draw values from the uniform distribution on this interval a to b. All right, and so if this is the average value here, then the integral of this entire thing can be estimated by taking the width of that interval, b minus a, times h bar sub n. Is that all right? And so whatever integral you have, you can just kind of estimate this and then multiply it by the width of the interval. All right, so so this is kind of the steps. Generate this from the uniform distribution. You're going to compute this. You're going to estimate this value. You're going to get h bar sub n, and then you're going to estimate the value of the integral. So integral hat, the estimate of that is going to be equal to b minus a times the estimate here. Okay, and if you kind of expand that in here, you're going to get this. All right, so here's just an example. This is the example that is in our textbook. So all of this, we got through basically one page so far. So at the bottom of the page here, we have this, okay? We're going to take the integral of this function, cosine of 50x plus sine of 20x. It's quantity squared, okay? So we're taking cosine and sine, and then, all right, so I plugged this into Wolfram alpha. So this is, if I have an integral I don't know how to solve directly, this is what I do. I go to Wolfram alpha and I plug it in and I say, what's the answer? All right, so Wolfram alpha says the answer should be 0.96520. All right, and it can be approximated with this. So apparently if you integrate it and whatever, you're going to get this. This is what the graph of the function looks like. So our graph matches what Wolfram alpha shows, so that's good. But basically, I just plug this in, right? We're just plugging in values of x, and if we estimate this via Monte Carlo integration, you know, here I'm going to say let's take 100,000 points, 10 to the 5. That's going to be n, and we're going to ask for 100,000 random uniform points. So I say big X is going to be my sample of 100,000 random uniform points, and then we'll compute the h applied to x, and then we'll take the mean of that, and we get this. Okay, I think I'm going to save the last 3 slides for Wednesday. Okay, so we'll end here for now. There's a couple more slides, but it's 10:50, so we'll end here. And so anyway, we get our Monte Carlo estimate, which is h bar n, and that's 0.9668. So it's close. It's the true answer is 0.9652, and we're getting 0.9668. Okay, so we're off by about a I don't know, 0.2 of a percentage point, something around there. Not a huge difference, but about a factor of about 0.2 of a percentage point off. So anyway, this is what we're getting. Okay, and the estimate of the integral would just be b minus a times that, which is 1 minus 0. So we're gonna get that. Okay, let's end here for now. Oh, last quiz answer. Last quiz answer is B as in bear. B as in bear is your last quiz answer. Okay, And we'll finish the last 3 slides on Wednesday. Okay, so last quiz answer is B as in bear. Okay, so we'll see you guys on Wednesday. Have a good day.